This video presents some background information on facies models, what they are, what they're used for, and how they're made. Facies models underpin a huge amount of sedimentology because they provide an integrated framework for interpretation of ancient depositional environments, based primarily on predictions that are made from modern depositional settings. So we'll spend a lot of time in this course creating facies models and using them to interpret depositional environments. I briefly mentioned the concept of a facies in the previous video, but here's a more formal definition. So a facies is just any sedimentary unit that can be defined by a suite of consistent characteristics, which can include its lithology, grain size, texture, sedimentary structures, fossils, or any other feature that can be observed. The unit has those particular characteristics because it formed in a certain depositional environment. Facies are typically named and described based on the observed features rather than on the inferred depositional environment. So you might have a facies called the pebbly trough cross-stratified sandstone facies, or a rippled siltstone facies, or so forth. You'll see some examples of these in class. So a facies model is just a group of multiple facies that are combined into some idealized vertical succession that represents the migration of depositional environments within a particular setting. For example, in a braided river, there can be a channel bottom environment, a bar environment, the overbank environment, so forth. Each of those environments would create a characteristic facies because the current velocity and the water depth differs, which leads to different grain sizes and bed forms, as you've learned previously. So facies models have been constructed for a wide variety of depositional settings, such as sandy braided rivers or wave-dominated deltas. We'll see many facies models throughout this course. So throughout as well, I'll try to use the term depositional setting to describe larger features like a braided river or a delta, and use depositional environment for a more specific region like the channel base within those broader settings. We see facies superimposed vertically when we look at a sedimentary succession. The beds are stacked one on top of one another, but of course the depositional environments that produced those facies were actually side by side on the original landscape. The overbank area is next to the channel, for example, but we may see its deposits on top of the channel deposits in a stratigraphic section. So the fundamental basis that allows us to relate the vertical succession of facies that we see in the rock outcrop to the original spatial relationships is called Walther's law. And simply, it states that the vertical succession of facies represents deposits from the migration of laterally adjacent sedimentary environments, at least in a conformable succession. So conformable means that there aren't any significant erosion intervals separating the different facies. In the example here, which depicts shallow marine environments, the beach sand is the shallowest environment, and it is next to or adjacent to the nearshore silt, which is next to the offshore clay and finally the offshore carbonates. Because beach sand and nearshore silt are laterally adjacent environments, their deposits are vertically superimposed in any of the sections. In section C or in section B or in section A, the nearshore silt is always on top of the beach sand. The offshore carbonates are above the offshore clay, which is above the nearshore silt, and so forth. We'll discuss in more detail the causes of these lateral migrations of environments, but for now it's just important to remember that the vertical succession of facies that we see in an outcrop, as long as there's no evidence for significant erosion, is caused by the lateral migration of adjacent depositional environments. When constructing a facies model, the first step is to identify erosion surfaces, especially those erosional surfaces within the sedimentary succession. As I just said, that's really important because Walther's law won't apply to facies separated by significant erosion. And even though one is on top of the other, they may not represent laterally adjacent depositional environments. In fluvial settings as well, erosional surfaces typically mark the base of any idealized succession of facies because the erosional surfaces mark the initiation of a new channel. Erosional surfaces in outcrop are often relatively easy to recognize because they're irregular surfaces. They may even look like a scour or channel that's been dug into the underlying unit. And they can also have a deposit called a lag. So a lag deposit is composed of coarse-grained materials, often like pebbles or shells, that are left behind when the erosive water flow that forms a new channel in a river carries away the finer-grained material. You remember the relationship between flow velocity and the size of the particles that flow can move, given by Shield's criterion. Next, we want to divide the sedimentary succession into consistently recognizable facies. There will definitely be some subjectivity in how you group beds together into a facies or how you split beds apart into different facies, because every bed is unique or has unique characteristics. But you will note when you're measuring sections that there are certain types of beds that reoccur again and again, and you might want to group those together into a particular facies. Once you do this, you can then interpret the depositional environment that would have produced that facies using your knowledge of sedimentary processes and modern environments. So for example, I've highlighted the channel base environment here. It's the deepest part of the river, and it typically has the highest water flow, and so it will therefore have the highest energy bed forms. In a sandy braided river, those are likely to be large 3D dunes. You remember that dunes are typically higher energy bed forms. 3D dunes more so than the 2D dunes is a general rule of thumb. Also, it turns out that dune height is approximately 1/10 of water depth, so deeper water will have bigger dunes and therefore bigger crossbeds. So what we would expect in this environment are fairly large trough crossbeds because they're produced by fairly large 3D dune bed forms in this deepest and fastest part of the water flow. Also, because this is the highest rate of flow, it will likely also have the coarsest grained sediments. So there's actually a tremendous amount of information that you can predict just from knowing how water velocity influences grain size and bed form type, and how you know the distribution of water velocity within your depositional setting. So finally, once we've identified the different facies that we think we want to recognize, we then try to group them together into a vertical succession. Is one facies consistently found overlying another, for example? What is the general transition as you move upwards in this succession? So it's important to note that because natural environments, of course, are rarely idealized, this characteristic succession may rarely or perhaps never be developed in its entirety. In this stratigraphic diagram here, there are three idealized columns shown at the bottom for three different parts of this sandy braided river system. But it's very possible that only part of the succession might be developed in any one of these columns. Maybe a new channel will erode through most of it and you'll only be left with the lower part of column C. Certain facies may not be developed all the time. For example, there doesn't have to be a sand flat or a cross-channel bar at every time. So, these are idealized, that they are not always represented, but nevertheless, they do provide an important framework for the comparison and the interpretation of depositional environments. And they're really, really a critical part of sedimentology and interpreting ancient depositional environments using these modern models as a guide for our interpretation.